Let ABC be a triangle with incenter I and circumcircle gamma. Circles omega b passing through B and omega c passing through C are tangent at I. Let omega b meet minor arc AB of gamma at P and AB at M. And let omega c meet minor arc AC of gamma at Q and AC at N. Raise PM and QN meet at X, and let Y be a point such that YB is tangent to omega B and YC is tangent to omega C. What we'd like to show is that A, X, and Y are collinear. So how do we go about proving this? Well, it definitely looks like Y lies on gamma, so that's our first conjecture. So how do we prove that Y lies on gamma? Well, we'd ideally like to show that directed angle BYC is equal to directed angle BAC. And we can't really do a whole lot with angle BYC here, so we might want to relate it to some of these angles. Angle YB something, where something lies on omega B, will work really nice because of our tangent lines. And we might think to use angle YBM because that's angle YBA, and we could do something with that. But in the end, we're literally just going to get angle BIM, and that angle is centered at I, and we can't do anything with that. So let's try angle YBI instead. So we have that directed angle YBI is equal to directed angle BMI because of the tangent lines. Similarly, directed angle ICY is equal to directed angle INC because we can just reverse the direction of each of these angles and get the same tangent thing. And now we have these two angles here, so we can go ahead and draw them in. And we want to somehow relate these two angles with this angle here. And now we definitely think about using this quadrilateral BYCI because the sum of the angles in that quadrilateral is 360 degrees, which is 0 degrees in directed angles. In particular, we have that directed angle YBI plus directed angle BIC plus directed angle ICY plus directed angle CYB is equal to 0. And we end up replacing the sum of these two angles here with BMI and INC. So we get directed angle BMI plus directed angle INC plus directed angle BIC. And if Y indeed lied on gamma, this would end up being directed angle CAB. And this is equal to 0. Rearranging, we end up getting directed angle BMI plus directed angle INC is equal to, we want to show it's equal to BAC plus directed angle CIB. Now we're going to employ a fact called the incenter-excenter lemma. Recall my video on that if you haven't seen it already, but pretty much what it states is that the circumcenter of triangle BIC lies on gamma, which means that it is a midpoint of the arc, minor arc BC. In particular, this means that directed angle BAC is equal to directed angle BMAC, and this, in turn, by the inscribed angle theorem, is equal to 2 directed angle BIC. So plugging that in, we end up getting 2 directed angle BIC, and then this is minus directed angle BIC, is equal to directed angle BIC. So therefore, we'd like to show that directed angle BMI plus directed angle CNI is equal to directed angle BIC. So how do we go ahead and show this? Well, we have these two angles here, So we'd like to show that they add to this bigger angle here. This suggests that we kind of split this angle into two parts and show that each part is these two angles. So we can end up approximating each part here. So this is approximation. And now we pretty much conjectured that this this divider between the angles is just the external tangent. And proving that this external tangent here is actually the divisor is pretty easy. We set G to be a point on this external tangent. Then we have directed angle GIB is equal to directed angle IMB. And reversing the angles, we get directed angle BIG is equal to directed angle BMI. Similarly, we have directed angle GIC is equal to directed angle INC. And adding these two, we end up getting the desired conclusion. Directed angle BIC is equal to directed angle IMB plus directed angle, or BMI, sorry, plus directed angle INC. Now that we know that y lies on gamma, we can focus on more details of the problem. First of all, we have these two unmarked intersections, so might as well draw them. We have, let's go ahead and call them W, and then call that one Z. Then now let's go ahead and draw MW and NZ because they are chords in the circle. And there we go. And now it definitely appears that MW is parallel to NZ. And if we take a closer look at this supposed trapezoid, we end up conjecturing that MWZN is an isosceles trapezoid. So how do we prove this? Well, the first step in proving that any trapezoid is isosceles, or proving that a quadrilateral is an isosceles trapezoid on the matter, is to show that MW is parallel to NZ. And now we know that I lies on the angle bisector of angle ABC. So that means that angle MBI is equal to angle IBW. And this means that MI is equal to MW. So those two lengths are equal. And this clearly means that MW is parallel to the tangent at I, this common tangent that I drew in earlier. Similarly, we note that NZ is also parallel to the tangent at I. Therefore, MW is parallel to NZ. Furthermore, since MI is equal to IW, M and I are actually reflections about the line connecting the centers, as are N and Z. And this is clearly enough to imply that MN is equal to WZ, so we have an isosceles trapezoid, as claimed. And now you guys might be noticing something about this external tangent that I drew in, forgetting about this isosceles trapezoid here. So let's go ahead and label that as W and Z. It definitely appears that this external tangent passes through X. And if this were true, then that would mean that we have these three lines concurring at this point here, X. And this line IX is a radical axis of omega B and omega C if this were to hold. And now we were looking for a radical axis with PM and QN on it. And this really makes us think that PM and Q is cyclic. Now our main efforts are improving that P, M, N, and Q are concyclic. And we'd like to do this by showing a pair of opposite angles have equal measure. And since we have angle PMN and PQN here, we'd like to show that directed angle PMN is equal to directed angle PQN. Let's first consider the PMN side of the story. Let's go ahead and erase that. we want to take the advantage of this isosceles trapezoid we found. Specifically, we want to use angle WMN. So let's split this angle to get directed angle PMW plus directed angle WMN. And now we have that angle PMW is equal to directed angle PBW plus and directed angle WMN is equal to directed angle ZWM because of our isosceles trapezoid. And directed angle PBW is equal to directed angle PBC because BW and C are collinear. And directed angle ZWM is equal to directed angle BWM. And now we note that directed angle BWM is equal to directed angle YBM because of the tangent lines. So that's PBC plus directed angle YBM, which is directed angle PBC plus directed angle YBA. Now let's consider the other side of the story, finding angle PQN. So in order to find PQN, we have this point C here, and Q is really related to point C, so we might want to try splitting it at point C. This gives us directed angle PQC plus directed angle CQN. And directed angle PQC, because Q lies on big gamma and so does P, it's equal to directed angle PBC. And this looks familiar. And CQN is equal to directed angle YCN because of the tangent lines. And this is equal to directed angle PBC plus directed angle YCA. And at this point, we note that angle YBA is equal to angle YCA because Y lies on gamma, as we previously proved. Therefore, angle PQN is equal to PMN, and therefore, these points are concyclic, as we claimed. Now we've shown that P, M, N, and Q are concyclic, and therefore X lies on the common external tangent of omega B and omega C by the radical center lemma on omega B, omega C, and the common circle of P, M, N, and Q, which I'll call omega. So I'll go ahead and draw that in. Sorry if it's kind of bad, but I'll go ahead and call this omega. Now that we have this, we can't really do anything with the common tangent at I because it doesn't pass through A. So now we'd like to show that PM, QN, and AY concur at the same point. This is an equivalent rephrasing of the problem. And this again makes us think of radical axes. So, and now we have this circle omega, and now we want another circle that involves the point APM and ANQ. And this motivates us to draw the circumcircles of AMP and ANQ. Now I've drawn in these two circumcircles, and now we'd like to show that Y lies on the radical axis of these two circles. And now we definitely suspect that these two circles are actually tangent to each other. And we can kill two birds with one stone here by showing that YA is tangent to it. We want to show that it's tangent to AMP. And by symmetry, it'd be tangent to QNA as well. So in order to show this, we like to show that YA something is equal to another angle. And we'd like for that something to be P because we could do a lot with that. So let's try showing that directed angle YAP is equal to directed angle AMP. First, we note that this is equal to directed angle YBP because Y lies on gamma. But now YBP is equal to, because YB is tangent to omega B, it is directed angle BMP. But this is directed angle AMP, and we are done. We have shown that YA is tangent to the circumcircle of AMP, and by symmetry, it is tangent to the circumcircle of QNA. Therefore, these two circumcircles are tangent, and Y lies on the external tangent. And now we apply the radical axis lemma on PM and Q and these two circles. We get that PM and NQ intersect on the external tangent AY. And therefore, A, X, and Y are collinear as we needed. So thank you so much for watching this video. Please subscribe if you'd like to see more videos.